Hi, my name's Mr. Ray. This video is about climate change. I first started looking into climate change when I was a high school astronomy teacher, and I was looking for a way to terraform Mars. I wanted to do a unit with my students and show them what it would take to terraform Mars. And what I wanted to do was add an ocean to Mars, and then add an Earth-like atmosphere, and then see how much carbon dioxide it would take to add to that atmosphere, or how much Mars would need to warm it up to Earth-like temperatures, because Mars is much colder than the Earth. And so I thought if we add enough carbon dioxide, it would warm the atmosphere. So I looked over the internet and I looked for an equation that would tell me exactly how much carbon dioxide I would need. I also did some tests with carbon dioxide and air mixtures to try to come up with an equation that would tell me exactly how much carbon dioxide was needed to raise Mars's temperature. Well, as I began to research and experiment, I began to discover some things that totally changed my view of climate change and the greenhouse effect. And I want to share those things with you in this video and in some further videos that will explain the things that I found. Well, this video I'm gonna call it. The title of this video is the giant greenhouse gas. Oh God. The title of this video then is going to be the giant greenhouse math mistake, and we're going to start with that. If you're at all familiar with climate change, you've probably heard of the greenhouse effect. And the greenhouse effect is that there's certain gases in the atmosphere that can absorb certain wavelengths of radiation coming off the Earth. Those gases are said to be then increasing the Earth's temperature 34 degrees Kelvin, which is 61 degrees Fahrenheit. So sunlight comes down, it warms the Earth then tries to release that heat into space. Greenhouse gases intercept some of that heat, and it's said that greenhouse gases warm the atmosphere 34 Kelvin degrees or 61 Fahrenheit degrees. Now, the average surface temperature of the Earth is 288 Kelvin or 59 degrees Fahrenheit. And so without greenhouse gases, our temperature would be 254 Kelvin or -2 Fahrenheit. That temperature 254 Kelvin is called the Earth's blackbody temperature. The temperature 254 Kelvin is known as the Earth's blackbody temperature. If the Earth was a perfect blackbody, a perfect absorber of radiation and a perfect emitter of radiation, then it's said that the Earth's blackbody temperature would be 254 Kelvin or -2 Fahrenheit. From now on, I'm just going to talk in terms of Kelvin, but I wanted you to see the Fahrenheit equivalents as we get started. So it's said that without greenhouse gases, the Earth's temperature would be 254 Kelvin, and since the Earth's average temperature, surface temperature, is actually 288 Kelvin, then it's said that greenhouse gases are responsible for warming it 34 degrees. That idea is based, unfortunately, the idea that Earth's blackbody temperature is 254 Kelvin. That's based on a calculation method error, and that produces the wrong blackbody temperature. Average radiation, what they're using to produce this is average radiation. They look at the amount of radiation that impacts the Earth, average it across the whole Earth's surface, and then use the average radiation to derive an average blackbody temperature. Blackbody temperature would be the energy from the sun alone, and so but they're using a wrong calculation method to do that. Average radiation is being used to derive average surface temperature. The mathematical reason why you cannot take average radiation and come up with average surface temperature is that radiation is a fourth power of temperature. So here's the formula for that. radiation is measured in watts per square meter, and it's equal to the Stefan-Boltzmann constant, which is a decimal point with 7 zeros, 567 times temperature in Kelvin to the fourth power. So you can see from this equation that radiation is a fourth power of temperature, also multiplied by a constant. Now, you cannot take average radiation then and derive an average temperature from it, because radiation is the fourth power of temperature. You cannot average fourth powers to find the average roots of those fourth powers. Let's take 3 and 5 as an example. 3, the fourth power of 3 is 81. All right, so 81 is the fourth power of 3. 625 is the fourth power of 5. Okay, now if you average the fourth powers here, you get 353. So you add these up and divide by 2, the average is 343. Okay. If you take the average of these fourth powers, you get 353. So that's the average of those two fourth powers. Add them up and divide by 2, you get 353. Putting that into the equation, well, actually, all right. If you take the fourth power, if you average the two fourth powers, you come up with 353. Add them up and divide by 2, you get 353. Now, the fourth root of 353 is about 4.33. And that's too high to be the average of these roots. These roots, the average of 3 and 5 is 4.0. And 4.33 is too high to be the average of those roots. So you cannot take the average radiation and derive a average surface temperature from it, just like you can't take the average of fourth powers and come up with the average of their roots and derive the average of their roots from it. So you can't take fourth powers and derive the average of their roots from it. Now, you say the mistake here is small, but when we get into real temperatures and real radiation amounts, you're going to see that error magnified. Now, the radiation from the sun at 10 degrees latitude. We'll start with the radiation from the sun at 10 degrees latitude. The radiation of the sun is the radiation from the sun is 930 watts per square meter. That, when you put it through this formula, that amount of radiation corresponds to okay. Let's scroll that up. Okay. Okay. Okay, that error is magnified when you apply it to real temperatures and real amounts of radiation. So for instance, if we take 10 degrees latitude on a blackbody Earth, at 10 degrees latitude, the amount of radiation is going to be 930 watts per square meter. That's what's not reflected. That's what's absorbed by the Earth. Okay, at 10 degrees latitude, this is the amount of radiation that would be absorbed by the Earth. That corresponds to a temperature 358 Kelvin. Make sure you can see that. Oh, not quite. Okay. All right, so 930 watts per square meter at 10 degrees latitude corresponds to a temperature of 358 Kelvin when you put it through this formula. Then take the radiation at 75 degrees latitude, or any other latitude you want, and at the end of this video I'll show you how to compute the radiation at each point on a spherical black body, the same distance from the sun as the Earth is. But I'll get into all the math at the end of the video. But for now, 75 degrees latitude would produce 352 watts per square meter of radiation coming from the sun, and that would result in a temperature of 256 Kelvin when put through the formula. So here we have one point on the Earth's surface at 10 degrees latitude, 930 watts per square meter at noon, okay, and then 75 degrees latitude at noon, 352. Now if you take the average radiation here, the average radiation between those 2 points would be 641 watts per square meter. So the average radiation, add those up and divide by 2, you get about 641 watts per square meter. And that would result in an average temperature of 326 Kelvin. So if you average the radiation, you would expect the average surface temperature to be 326 Kelvin. But if you add these two up and divide by 2, the real average is only 307 Kelvin. So you can see the real average surface temperature on a black body is much lower than you would expect if you first average the radiation and then try to derive the average surface temperature. You end up with something that's too high. Now, this becomes even more extreme when you factor in temperatures on the dark side, on the side away from the sun. So the sun's shining on one side of the black body. On the other side of the black body, there is no sunlight coming in, and so you have to factor that in to, no matter if you're taking the average surface temperature, you have to factor in the dark side as well. So now we'll look at a dark side temperature. Okay, the dark side temperature is, we'll put dark here. Okay, so the dark side temperature is going to be zero, has zero radiation because it's blocked from the sun, and so it has a black body temperature of 0 Kelvin. So if we take a point on the light side at 10 degrees latitude and average it with another point on the dark side, well, if we average that radiation, the average radiation would be about 465 watts per square meter. And that, if we then try to derive the average temperature of those 2 points, the average temperature would be 301 Kelvin. So if we average the radiation first and try to derive an average temperature from that, the average temperature would be 301 Kelvin. But if we take the real average temperature when you add these two surface temperatures up and divide by 2 is only 179 Kelvin. So you can see that the magnitude of the error is increasing when we factor in the dark side. And this is why the idea that the Earth's temperature is 254 Kelvin is an error, because what they're doing is they're averaging all the radiation points. Okay, all the points of radiation they're averaging first and then deriving an average temperature from that, and they're always going to come up with something that's too high. So this is the wrong So this is a calculation method error, okay? And it's based on the idea that you cannot take the average of fourth powers and derive an average of the roots. Now, when the wrong method is used and they average radiation first and then try to derive the average surface temperature from it, that's where they come up with the idea of 254 Kelvin being the black body temperature of Earth. It's based on a wrong method of calculating the average surface temperature. This is too high. When you take every single point on a black body sphere and you average it point by point, it only comes out to 143 Kelvin. And so the idea that the Earth, so this is the correct black body temperature because it's done in a point by point method, including all the points on the dark side, all the points on the light side. You'll come up with an average of 143 Kelvin, and I'll show you at the end of the video how to do that math. But the point here is that this is too high because it's based on averaging the radiation first and then trying to derive an average surface temperature from that, when if you go point by point, the real average surface temperature on a black body for Earth is about 143 Kelvin. So what does that tell us about global warming or the greenhouse effect? What that tells us about the greenhouse effect is this. We were thinking that the greenhouse effect raises the temperature from 258 to 288 Kelvin, so that there is 34 degrees Kelvin of greenhouse gas warming, all right, or of global warming so far, 34 degrees Kelvin, to go from the black body temperature as it's calculated up to the average surface temperature of Earth. The reality is something is warming the Earth not from 254 Kelvin up to 288 Kelvin, but something is warming the Earth from 143 Kelvin all the way up to 288 Kelvin. So instead of 34 degrees of warming, Earth has to be warmed 145 degrees Kelvin. And 145 degrees Kelvin is too much warming to attribute to any kind of greenhouse gases effect. So the idea that greenhouse gases warm us 34 degrees is based on a fictional black body temperature. The real warming is from 143 Kelvin all the way up to 288 Kelvin. And there's a different mechanism that has to do it because greenhouse gases are not powerful enough to do that kind of warming. There is a different mechanism that is powerful enough to do it. Before we take a look at that mechanism, though, there's another fact that we have to include. All over the Earth, the average rainfall is 990 millimeters. Okay, 990 millimeters of rainfall. Before that rain falls, it starts out as liquid on the ground and it has to be evaporated into the atmosphere. The rainfall first has to be evaporated. In order to get 990 millimeters of rainfall, the water first has to be evaporated from the surface, okay? And when water is evaporated, it absorbs extra heat energy called the latent heat of vaporization. So heat energy is absorbed from the surface, then the water vapor travels up, releases that heat at the level of the clouds away from the surface, to go back to being a liquid and then falls as rain. So in order to get 990 millimeters of rainfall, you first have to evaporate all that water, and that carries heat, that cools the surface and carries heat and releases it away from the surface. When you calculate how much it takes for 990 millimeters of rainfall annually over the whole surface of the earth, you find out that the earth is being cooled 192 degrees. There's 192 Kelvin degrees of cooling that's happening to evaporate all that water at the surface and turn it into vapor so that it can rise up, release the heat away from the surface. That results in a total cooling, an average total cooling of 192 Kelvin, and this is constant cooling. So there's an average constant cooling going on of 192 Kelvin. So not only do we have to raise the temperature up 145 degrees to get to 288 Kelvin, we have to go. Okay, so to get to 288 Kelvin, we not only have to go up 145 degrees, but we also, the earth is being constantly cooled 192 degrees. We have to go up another 192 degrees so that evaporation can constantly cool it back to its average temperature. So not only do we have to go from 143 up to 288, we also have to go 192 degrees further and come back down via evaporation. So evaporative cooling is bringing us down 192 degrees from another temperature. And so we need a heating mechanism that not only heats us 145 degrees, but we need a heating mechanism that takes us all the way up to this level so that 192 degrees of constant cooling can bring us back down to our average temperature. And so there is a heating mechanism that can do this for us, but it's not the greenhouse gases.